Howdy, 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 howdy. All right, we're in Unit 3 and we are on Topic 1. And this is probably my all-time favorite unit, Light and Optics, or Light and Energy Systems. It is a fantastic unit. I think you guys are going to have a lot of fun learning about this stuff. Lots of cool stuff to look forward to. Here are all of our topics. Okay, we have looked at this a little briefly before, but Topic 1, we're going to talk about light. What is it? Okay, and then these are the other topics we will be going through. Okay, Topic 3 and Topic 4 is where we're going to spend a lot of time. This is where we're going to be learning not only about refraction, so the bending of light, as well as lenses and vision, but more importantly, the anatomy of the mammal eye, or even the human eye. Okay, so we're going to learn about the anatomy and hopefully do a pig or a cow eyeball dissection so we can get a first-hand look at the structures in those eyes. So, really cool unit, lots to look forward to. So let's get going. Of course, you've got your follow-along notes with you, you've got your pencil ready to rock and roll, and of course, you are scribbling in these fill-in-the-blanks. Some of them are sentences, most of them are just fill-in-the-blank words, okay? If you need to pause, obviously pause. Pause so you can write those in, so you have good notes to study so that you can really crush these tests and quizzes and exams and all this fun stuff. So anyway, what the heck is light? Well, light, it's a form of energy. And really, it's the form of energy that you can see. Okay, and that's how we're going to define it. So we know that from any light source, that could be the sun, it could be a match, it could be, anything that's giving off light. And we would say that those light sources are radiating light. Okay, light spreads out and we call that radiation. Okay, so think of it as if you hold up your fingertip even, and pretend the tip of your finger is a match and it's lit. Okay, imagine how that light is radiating from it. It's going in 360 degrees in a full complete circle all the way around it. So light is radiating off it in all directions. Okay, and when energy is radiating, and it's not just light energy, there's lots of different types of radiation, but when energy is radiating, we would say that that energy is traveling in waves. That might not make a lot of sense right now, but it will as we go to other topics. But for now, just know that energy radiates in waves. Okay, so it says down here, what are some sources of light? What do these all have in common? Well, the sun is probably the most commonly known source of light. We get all of our solar energy, and really life is dependent on the sun. Okay, so as I said already, a lit match, your phone screen, a TV screen, LED lights, light bulbs on the top of our ceiling, fluorescent lights. Okay, these are tons of different light sources, and what do they all have in common? Well, the energy that they're giving off, the energy that they're emitting, that light energy is radiating, and that radiating light energy is traveling in waves. Okay, so natural and artificial light sources. So when we think of the word artificial, I just want you to think man-made. So is it something that a human being has invented or created? So obviously like a TV screen or a Chromebook screen, those are giving off light. We wouldn't find them naturally in nature. They are man-made, so we would say they're an artificial light source. On the flip side, a natural light source is something that you would just find naturally in nature. Like if you're an alien from Mars or wherever, exploring Earth, the light sources you would find in nature, okay, we would call a natural light source. So you could think of, say, like a lightning strike. Okay, we would find that naturally in nature. Down here, there's a little GIF of a firefly, right? That happens naturally in nature. Okay, fire, same thing. That's natural. We would find that in nature. Now you might be thinking, well, hang on, Lewis. You said if it's man-made. Well, what if a person started a campfire? They made that fire. Yes, that is true. We would still say, even though a person made that campfire, fire is still natural because we find that naturally occurring in nature. Okay. Ooh, that got messed up. Pardon me. Let me just move this properly. There we go. Aha. Sorry about that, guys. There we go. Cool. So take a look. Fireworks, obviously, man-made. Okay, you don't find fireworks in nature, unfortunately. That'd be pretty cool. But man-made, and that's pretty darn spectacular. Holy smokes. Jeez. My goodness. That's right, guys. I'm going to have to fix that after. I apologize. Anyway, it's supposed to look like this. Lightning strike. Cool. Occurs naturally in nature, so it's a natural light source. There we go. Okay, so we have the first basic principle of light. And the first basic principle states that light is a form of energy. Okay? Now, if you're kind of wondering, like, what the heck is energy? Well, before we answer that, think all the way back to our first unit where we're talking about matter. Well, what is matter? Matter is anything that is made up of particles. So there's little tiny particles that combine together to make this substance or this thing. Okay, that's what matter is. Energy is not the same as matter. Energy doesn't have particles in it. Energy, and this is a weird way to define it, and you're probably going to shake your head at it because I know I did when I was your age, but energy is the ability to do work, to make something happen or make some kind of a change. We're going to explain that a lot more later in the unit. We'll get a better answer than that for now, but just think of energy as the ability to do some kind of work. And light is a form of energy. The cool thing about light is that we can transfer it or turn it into different types of energy. So take a look here. We have solar energy coming down to hit these solar panels. And of course, we're converting that solar energy into electrical energy. Here, we've got an incubator. So if I wanted to put in some eggs, okay, and incubate them, that solar energy is being turned into thermal energy for those eggs so that they can grow and hopefully hatch into a chicken that I will eventually eat. Down here, right, we've got trees taking in this solar energy through the process of photosynthesis. That solar energy is converted or transferred into chemical energy that will then be used as, to create sugar and the energies that this tree needs to grow and function and be alive. There are 4 different types of light sources that we can classify every single light source into. So any kind of light source you can think of right now will fall under one of these 5 different types. So there's incandescent, and that's an example of it. We're going to go into greater detail, don't worry. There's fluorescent. There you go. If you look up in the ceiling, you can see more examples of these. There's phosphorescent. I don't know if you guys had any of these growing up. Well, I guess you're growing up right now. But me growing up, I had these glow-in-the-dark stars and like moons and stuff I had over the ceiling of my roof. Okay. Chemiluminescent. Oof, ouch. Bam. And lastly, bioluminescent. Cool. So 5 different types of light. What the heck do they mean? Well, here we go. Incandescent. Incandescent light sources are when something gets so hot that it glows. So here's an example of a welder. Okay, so he's heating up these 2 chunks of metal to fuse them together. That's what welding is. And to do that, you have to heat up the metal so that it melts. And then the liquid metals fuse together. And as it's heating up so hot, it gets literally red hot. It begins glowing. We would say this is incandescent. Old school light bulbs, which are kind of becoming a thing of the past, but they have inside something called a filament. So right here, it's hard to see, but it's kind of like a spring. It's like a wire that goes around, round. As the electrical current comes through, that electricity is going through the filament, heats up that filament to the point where the filament is white hot, and it becomes incandescent, it's glowing, and it gives off light. Okay? So it's so hot, it glows. Incandescent. The advantages of incandescent lights is that they're cheap. They're really cheap and inexpensive to build. Okay, so that's good. And they're also easy to dispose. You just throw them in the trash. You don't have to worry about toxicity or anything. They're cheap and they're easy to dispose. Disadvantage, though, is that they're inefficient. There's a lot of wasted energy. So the electricity that comes into this light bulb, not all that electrical energy is turned into light. Most of that energy is actually wasted as heat. Touch a light bulb and see what I mean. Actually, don't do that. You'll burn your fingers. Okay, so it's inefficient. We're wasting electrical energy. In an energy conversion, this is actually what it would look like for this light bulb. The electrical energy goes into the light bulb. Electrical energy goes through the filament, heating it up, so thermal energy. Thermal energy means heat energy. And once it gets to a certain point and it's hot enough, that thermal energy is converted into light energy. Okay? And actually, you know what? I just want to fix this because this isn't quite right. There. So now electrical energy is turning into both thermal energy and light energy. Cool. Fluorescent light bulbs. Out of the 5 types of light sources, I would say this one's probably the trickiest to understand. And when we think of fluorescent lights, I mean, we've seen them all our lives. They're in the ceiling of Walmart or really most stores. They're in the ceilings of our school classrooms, okay? They're these long tubes that give off light, okay? They often kind of hum as well, okay? But how the heck do they work? Well, a light source that uses electric current through mercury vapor to create ultraviolet waves. These waves cause phosphorus coated on the bulb to glow, creating light. What the heck does that mean? Well, if we look down here, this is a little fluorescent light. We're looking on the inside of it, okay? So inside this tube, there's mercury vapor. Okay? When you flick on the light switch, an electrical current goes through this light bulb. Okay? And that electrical current doesn't just go from one end to the other end. It actually it goes through the mercury vapor particles. Okay? And it excites these particles where it reflects back ultraviolet waves. You've probably heard of ultraviolet because when you're putting on sunblock, you want to have ultraviolet protection. Anyway, these ultraviolet waves reflect back outside of the light bulb, of the fluorescent bulb, and as it goes through the glass, that glass is coated with phosphorus, and that phosphorus will begin to glow. So if you've ever been in like a dark room and someone turns on a black light and like your white shoes want to glow, anything that you're wearing is white or a light color, it looks like it's glowing. That's essentially what your fluorescent light bulbs are doing. They're glowing just like white shoes next to a black light. Okay, that mercury vapor is giving off ultraviolet waves, and that ultraviolet waves make that phosphorus coating on the inside glow. Okay. So an advantage of this: these are very energy efficient. There's not as much wasted electrical energy. As much as there is an incandescent at least, okay? And that's why you see these in department stores, in schools, because that way their power bill isn't as expensive as it would have been. Disadvantage, they can be toxic, right? This mercury vapor isn't good for us, okay? It's not just straight up mercury, it's a compound, it's mixed with other stuff. But this mercury vapor still isn't good for you, okay? If you break one of these fluorescent light bulbs, you want to be careful. You don't want to clean it up with bare hands. You'd want to use latex gloves. Okay, and because it's toxic on the inside, it can be hard to dispose of these safely. Most people just throw them in the trash, but you probably shouldn't do that because you don't want to get that mercury vapor on people accidentally. Secondly, the bulbs are more expensive than incandescent, so they can be expensive. Okay, energy conversion, there is electrical energy converting into light energy. Let me fix this as well. There is still thermal energy being created as well. Just not nearly as much thermal energy as the incandescent. Here's another example. So a beam of electricity, it's exciting these mercury vapor particles. They give off ultraviolet rays, goes through the phosphor coating, and then the phosphorus coating glows. And we have visible light. Cool. Next one, phosphorescent. Okay, this is anything you've ever had that glows in the dark. It's phosphorescent. And how the heck do these things work? Well, they're a certain type of material that is able to absorb light energy on their own. So if you ever had like a glow-in-the-dark action figure or something, you're super excited, you take it in the dark and, oh, it's not glowing in the dark yet. But then when you take it back outside, maybe out in the sun, that phosphorescent material absorbs the light energy, and then when you take it back in the dark room, then it will glow. okay? So it stores light energy, and then it releases it when it's in the dark itself, okay? So here's an example down here of some laces that glow in the dark, okay? We would say they're phosphorescent, okay? Here's another example, like this is an old cereal box, comes with toys. I don't know if cereal boxes still do this. They used to come with toys all the time. It was awesome. But anyway, these monster heads, okay, these would be phosphorescent. You put them out in the sun for a while, and then you bring them back into a dark room, and they glow in the dark. They're phosphorescent. They absorb light energy. Okay. Advantage of these? Well, it's free. You don't need to plug it into an outlet. You don't need electricity to make this light source work. Okay. So it's free, and you don't have to plug it in. That's a huge advantage. But a disadvantage is that it's not going to be as powerful as fluorescent. It's not going to be as powerful as incandescent. Okay, it's not going to give off a huge light source. It's a reason why our headlights and vehicles aren't phosphorescent, because they're just not strong enough. Energy conversion. We have light energy hit the phosphorescent material, and that light energy gets stored, and then it's re-released as light energy once again. Cool. Chemiluminescent. So chemi, this root right here, this prefix, chemi, think chemical. Chemi, chemical. So it's a chemical light, essentially. Okay. So a chemiluminescent light source is when you mix two or more chemicals together, creating some kind of chemical reaction, and a byproduct of this chemical reaction is releasing light energy. So take a look at this GIF right here. We've got luminol and a couple other chemicals getting mixed together, and they are reacting with one another, giving off light. Pretty neat. Notice how it's really intense when they're first mixing, and as the reaction occurs, it gets progressively darker and darker. That's because the chemical reaction is at its strongest when they're first mixed, and then the chemical reaction is slowly ending. Okay, anyway, other examples other than this luminol reaction, think glow sticks, right? Glow-ons, right? You crack the glow stick, that creates that chemical reaction, and that's why we have glow sticks. Advantage, again, it doesn't require an active electricity source. You don't have to plug it into a wall or anything. That is awesome. Disadvantage is that it's hard to control how much light is produced. Like, notice it's really bright at the start and then gets darker, okay? And secondly, kind of like our phosphorescent light sources, it's not super strong. Not a super strong light source. Energy conversion would be chemical energy transferring into light energy. And lastly, guys, bioluminescent. Look at the suffix here, bio. When we hear bio, think biology. And biology is the study of the body, okay? So, or organisms rather. So organism luminescent or organism light, this is light that comes from organisms, that comes from living, breathing organisms, okay? Well, not necessarily breathing, but living organisms, okay? How the heck do they do this? Well, it's similar to chemiluminescent. These animals have chemical reactions inside them, their cells that will emit light. So obviously human beings, we are not bioluminescent. We do not give off light, unfortunately. That'd be pretty darn cool, but we don't, okay? But this thing absolutely is bioluminescent. You can see how it's radiating light even in the depths of the dark ocean, okay? Certain types of fungi, right? This is sped up, of course, but certain types of fungi also are bioluminescent and give off light. There's chemical reactions happening in its cells that are emitting this light. Look at this guy too. He's a beetle. You can see his light source right here on his rear, not a beetle. What am I saying? There's a worm. Towards the back of its butt. Okay, certain types of fish. Isn't that cool? Okay, awesome. Fireflies, of course, are probably the most commonly known bioluminescent animal or organism. An advantage, the organism doesn't need to find an artificial light source, so these guys are their own light source. We need a flashlight. They don't. Pretty cool. Secondly, some of these organisms use their light sources to attract their dinner, to attract their prey, so that's pretty cool. Disadvantages, though, there's limited use. I mean, it's not like they have flashlights, right? So it's not the most powerful light source. Secondly, Sometimes these bioluminescent light sources can be an attraction for predators. So whoever wants to eat this guy, pretty easy to find him, right? You can just see his eye. Energy conversion, it's chemical energy being converted into light energy. Okay, the ray model of light. The ray model of light states that light travels in rays, and we can think of rays as straight lines. The proof that supports this model is that when we have an object in the path of light, it leaves a shadow on the wall, okay? And because the shadow is the exact same outline as the object, we can see how the light is traveling in a straight line, okay? Right here, the rays of light can't travel because they're not going through this object. The light rays that are going here stop. They can't pass through, and that's why there's a shadow. The shadow is really the absence of light, or the absence of rays of light, okay? And again, as we said earlier, light radiates in all directions, okay? And it's radiating out in straight rays. That's what the ray model is teaching us. Light travels in straight lines, called rays. Here's another example. We got two dudes here. Light sources right there. These guys are just normal sized people, but look at the size of their shadow, okay? This is based on how far they are from the wall, as well as how far they are from the light source. And we can see the angle of how the light is traveling makes them look like they're a couple giants, okay? And again, we can think of how the light is traveling in straight lines, okay? If it was bending, like if the light was bending somehow on its own, these shadows wouldn't look like these guys. They would look maybe more like a rectangle or a circle or something, right? But because these shadows look pretty much exactly like these guys, we can see how light travels in straight lines, okay? Also, if we come back to this slide, we can see how this object, it's this big, but the shadow is much bigger, okay? Because of the angle of how the light is radiating from the light source. Okay? Awesome. And again, we move the light source back further. We can see how the shadow gets smaller. We move the light source closer, like it is here. We can see how the shadow gets bigger. Okay, just another one for you to look at. Again, light's traveling in straight lines called rays. Okay, shadow looks a bit bigger than the object based on the angle of the light. Okay, and lastly, guys, we have three different types of surfaces, and these different types of surfaces react to light in different ways. So an opaque surface, when light strikes it, it either reflects off or gets absorbed. We can't see through it at all. It's opaque. So look at the wall in whatever room you're in. That wall's probably opaque. You can't see through it. Translucent means that you can kind of see through it, but not fully. Okay, so kind of like a foggy window or something. Okay, we would say that's translucent. And then transparent, you can see through it like it's invisible. So like a window or glass. Okay, we're going to talk about this later in other topics. Why these surfaces react the way they do. Why transparent is basically invisible. Why translucent is kind of half. Why opaque is, you can't have light go through it. We'll discuss that later, but it depends on refraction, reflection, and absorption. But again, that's for something later. All right, guys, thanks for following along so well. Thanks for filling in your follow-along notes. And thank you for reviewing these notes as we approach our first quiz. Hint, 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 because it's definitely coming. Thanks, guys. Have a good rest of your day. Bye for now.